On sequences and series. Now that the volume's on, welcome back for a continuation on sequences and series. Today we're going to talk about something called the recursive definition. Recursive definition, I was trying to make a joke about cursive writing there, but nothing came up, so we'll just stick with recursive definition there. Nothing to do with how you write. Recursive simply means that you're dealing with something that was preceding without knowing enough information to come up with what we talked about last section, which is actually called an explicit definition or explicit formula. This is a recursive formula. And there's no real way to explain it other than to jump right in. Let's say I give you the first term to be 5, and I tell you that all preceding terms, or all following terms, are formed by taking the previous term, t sub n minus 1. Let's say it's being multiplied by 4, and then you subtract 3. Okay, this simply says take 4 times the previous term and then subtract 3. So think about that. 4 times the previous term. T2 would then be 4 times 5 minus 3, which would be 17. T3 would be 4 times 17, and then minus 3. T sub 4 would be 4 times 65, and then minus 3. So that's 240, that's 260, so 257 if I'm not mistaken. So you can see how this would be kind of annoying. If you want to find t sub 10, you're going to be going for a while. So the recursive definition is a bit antiquated in the sense that you need to know the immediately prior information to find the following information. So that initial condition is important. You need an initial condition. And then, and only then, can you use the rule, the equation, the recursion equation, or the rule, recursion equation, or the rule that allows you to go from that previous term to the next term. And you can certainly take some recursive equations and turn them into the explicit equations. Let's take 25, 20, 15, 10, dot, dot, dot. So recursively, you know the first term is 25. And to find the following term, you're simply going to take the previous term and subtract 5. Okay, that's the recursive equation. To find any term, t sub n, any term, you take the previous one, or the one you have, and subtract 5. You take the previous one and subtract 5. So to find the fifth term, I'm going to take the fourth term and subtract 5. And I get 5. To find the sixth term, I'm going to take the fifth term and subtract 5. Okay, and the seventh term then will be 0 minus 5, and then it'll be negative 5 minus 5, then it'll be negative 10 minus 5, then negative 15 minus 5, so on and so forth. This, remember, is the recursive equation. Okay, explicitly, the first, well, any term t sub n is the first term minus 5 times n minus 1, or 25 minus 5n plus 5, which is 30, minus 5n. Okay, so there's recursive versus explicit. And again, kind of capping on what I was talking about in the previous video about this being very linear-like, this looks like a y-intercept and slope. And in fact, if you're graphing it, this is what they are. But remember, the y-intercept occurs when your n or x value is 0. In this case, n value is 0. We don't have a t sub 0. So 30 is not the beginning of my sequence, even though it's your quote-unquote beginning of your graph, your y-intercept. Okay, 30 is just how I get my first term. It's 30 minus 5, right? Minus one term, one difference. So 25 would be my starting term, the starting dot on my graph. So let me show you how recursive can be somewhat useful in certain instances, because it is nice for when you're doing mortgage amortizations and if you want to see how population is growing from year to year, and it's growing by a percentage or something like that, for instance, is very useful to do that. Our calculator can actually be used as a recursive machine, and in fact, a lot of the programming in calculators are done by recursion equations. They're called loops. So if you have your calculator handy, it'd be kind of beneficial to follow along here. So let's say you have a population of 1,000, and I'm going to hit enter here, and you know it grows by 1%, or let's go 10%. It grows by 10% every year. So recursively, I'm going to take the current population and multiply by that 10% growth, in other words, 1.1. There's 1 year later. So T1 is 1,000, T2 is 1,100, T3 is 1,210, T4, T5, T6, T7, T8, T9. And notice it's constantly taking the previous answer and multiplying by the next thing. So this is a geometric recursive formula because we're taking the previous thing and multiplying it. Arithmetically, let's look at this first example I did right here. So 5 is my first term. Boom, enter. And now I'm going to take 4 times my answer. So 4, second, answer, minus 3, enter. Dun, dun, dun. There's 17. Enter. 65. Here's the test. Did I get it right? Boom, 257. Okay, again, notice it's doing it recursively. It's taking 4 times the previous answer and minus 3, and we can go on and on and on. We can go all day with this, man, all day. All right, so there's the recursive equation. Not much to it. You just need to know a little more information, and it's not nearly as efficient as an explicit formula would be. That is our recursion equation, and we are done with this section for today.